Hi, welcome to Complex Analysis. This is the fifth session on Cauchy theory. Today we shall start having a deeper look at Cauchy integral formulas, and we will compare with the standard proofs in other books, even in my own book. And then we shall derive the so-called Cauchy estimates and explain why it is significant and give a typical application. And later we shall look at the so-called mean value theorem. I think it's due to Gauss. Hopefully we should be able to do all these things within, let's say, about 15 minutes. Let's hope. So let us recall Cauchy integral formula. So U is star shaped open set. That's not actually needed. Open set F from U to C, holomorphic. Okay. Then fix Z0 in U and an R positive, or make it R so positive so that B Z0 R is contained in U. Then for every 0 less than or less than capital R, let us look at gamma t equal to Z0 plus R e power I t, 0 less than equal to t less than equal to 2 pi. Okay, when we found out for every z in B Z0 of R, okay, the nth derivative of f at z is n factorial by 2 pi I integral over gamma of f of w by w minus z to the power n plus 1. Okay, now I would like to point out how we got this formula. I mean, I explained it in the earlier lecture, but it's worth noting because it was so fast you might have missed. Okay, a non-trivial result, we got it so easily because of our earlier work. Okay, so let's try to understand that. So notice that this is for any n greater than or equal to 0. Therefore, this is usually, I call it CIF, Cauchy integral formula for derivatives, and CIF is the case when n equal to 0. When n equal to 0, we know f of z is 1 by 2 pi I over gamma f of w by w minus z. That's it. If you want, put dw, but usually I may not do that, but anyway. Yeah? Okay, how did we get that? Okay, we got it from Cauchy integral formula. Let us understand. We got Cauchy integral formula, right? We said, with the earlier assumption, we said f of z is integral over gamma 1 by 2 pi I of f of w by w minus z for z in B Z0 of R. Okay, now this is a Cauchy type integral, what we call Cauchy type integral. I am just repeating the earlier argument, okay, so that you can compare and contrast with other approaches to Cauchy integral formula. Okay, this is very important. Let us recall, if gamma is a path in C, okay, that is okay, maybe if you want gamma at AB to C, a path, and f is a continuous function from the path gamma, maybe make it g, continuous function. Okay, this is different from my earlier notation, right? Then define f of z equal to integral of gw by w minus z over gamma, where z is not on gamma. When we prove this is analytic. Okay, yeah, there is a slight disturbance, and so let me continue. So we wanted to show how we proved the Cauchy type integral defines an analytic function. I just touch upon that and then derive the formula. So what we did was, if f of z is integral over gamma of g of w by w minus z dw, then we found out it is of the form Cn. Okay. Okay, z minus z naught to the power n. Okay, choose a z naught not in gamma and z in some b z naught of r contained in c minus gamma, etc. Right, all such things where cn's are given by integral over gamma of g of w by w minus z to the power n plus 1, w minus z naught to the power n plus 1 dw, right? But in the power series we know what cn's are. Okay, cn's are nothing other than, right, nth derivative of this at the point z naught by n factorial. Are you following? Okay, right, therefore nth factorial of z naught is, so nth derivative of z naught is n factorial integral over gamma of g of w by w minus z naught to the power n plus 1. This is true for every z naught not in gamma, right? Yeah, right, and hence we can write for every z not in gamma, I can write nth derivative of this at z is n factorial into g of w by w minus z to the power n plus 1 dw. So now return, okay, f is a holomorphic function from an open set U to C, okay, and fix s z naught in U, and so that b of z naught r is contained in U, and for 0 less than r capital R we have gamma of t equal to, as usual, z naught plus r e power it, etc. Right, 0 less than or equal to t less than or equal to 2 pi. Right, so what we had was for every z in B, z naught of r, f of z is 1 by 2 pi I over gamma of f of w by w minus z dw. Right, so this is again a Cauchy type integral. Therefore by this result, okay, implies nth derivative at z is n factorial by 2 pi I integral over gamma of f of w by w minus z to the power n plus 1 dw. Okay, right, so stop to think. So how did we got this so cheap? Because our earlier work. Okay, what is our earlier work? Our earlier work was that on power series we have shown that any power series is term was differentiable, and from that we concluded the nth coefficient Cn is nth derivative of f at that point center of the power series divided by n factorial. That's one observation. Second observation is, if whenever a function is given as a Cauchy type integral, then that is an analytic function, and we know how to write down the local power series for that. So combining these two things, we got it. Okay, please understand the traditional method. Okay, pause, review, proceed. So you should know how cheap you got it. It is not cheap because you had already done all the hard work earlier. Okay, the traditional books will try to prove in a slightly different way. They will write f of z plus h minus f of z by h and try to show it converges to f of w by w minus z whole square dw. Okay, by careful estimate. Okay, you can go through that in books, and so many of the textbooks may use this approach. So you may find, and hence then by induction, then proceed by induction to get CIF-D. Okay, so many of you might have been going through this proof, and you may be wondering, the proof which we got seemed to be so cheap, and without any work we got it. But don't let our approach fool you, because I banked upon our thorough knowledge of power series. In fact, many complex analysis books may try to talk about power series etc. after Cauchy integral formula. Okay, and that's why they have to do little more. Okay, please understand. There is also a third proof which uses Leibniz rule under integration, rule of differentiation under the integral sign, but that proof needs a, if f is holomorphic, f dash is continuous. Okay, this fact is needed. Okay, then only I can go through that proof. But in our approach, just because it's Cauchy type integral, we already know it's analytic. That means it's infinitely differentiable, therefore f dash will be automatically continuous. Okay, so our proof perhaps is the conceptually easier and simpler. It tells you why things worked the way they are. Okay, so please take some time, review. So I want to give a typical example. Okay, application of CIF-D. See, it says something like this, right? F of n of z is n factorial by 2 pi I integral over gamma. Remember, all these things are circular paths. I don't want to keep repeating with standard parameterization. That means it goes in the anti-clockwise direction, etc. Right? So the way we are focusing is, I am given a holomorphic function f. I then my nth derivative of f of that holomorphic function is given by an integral of this kind. Okay, that is nth derivative is given as a path integral. Is given as a path integral. Namely this path integral. Right? Right. But this is one side of the coin. See, whenever you have some kind of an identity or equation, there are two sides. Right? So there are always two uses of such a thing. If you had gone through some of my lectures on real analysis, I have pointed out many places. Okay, the second thing is, think about it this way. I am given some path integral. Okay, a path integral is given, right? If I recognize this as a CIF-D, that is, it's a Cauchy integral formula for derivatives for suitably defined functions and etc., then I know how to compute the derivative, compute the path integral. How to compute the path integral? I only have to compute whatever it is, a CIF-D, some whatever it is, something like nth derivative at some point z0, maybe 2 pi I etc. thrown out. Okay, are you following? Okay, I will start with a very trivial example. So let us say that I have something like a circle, okay, of radius 1, radius 2, right? It's a standard gamma 2 e power it. Then I want to find, this is my gamma, okay, and let us say I want to find what is e power z squared by dz. Okay, now I can notice that this is a Cauchy type integral for f of z equal to e power z and by z squared, therefore it's a second derivative. This is the first derivative, that is f dash of z at 0 times 2 pi I, which is This is e power z, therefore e power z derivative is e power z, z equals 0 is 1, therefore the answer is 2 pi I. I hope I did correctly. Maybe I went too fast. Let me just make sure. So this is f of z by z minus 0 whole squared over gamma. Therefore this is the first derivative of f at 0, that is e power z, and then multiply with 2 pi I, right? You understand? Right. Let me do a slightly more complicated example. So pause, review, proceed. There are a lot of small examples like that. So the idea is that you should be able to recognize it. Okay. So let us look at the function. Okay, let me just look at, I have assumed two circles. Let us assume this is half and this is 1. Then I have a circle of radius half centered at this, and there is another circle again which is tangential and centered at 1. Centered at 0, this is centered at 1. Okay, call this gamma 1. Let us assume gamma 1 goes from here, that is starts from half and goes like this, and when it comes here and after that it decides to go this way. Okay, it's like a figure of 8. How does it start? It goes like this and comes like this. Okay, that's my gamma. Okay, and what is my function? My function is the path. Okay, the path integral is gamma z squared plus 1 by z squared into z minus 1 dz. Yeah, now you can see it's not directly of the form, but then there is something very interesting happening. Okay, I want to cast this as CIF-D. Okay, now notice that this one for the path gamma 1, so this integral is integral over gamma 1 plus integral over gamma 2. Is that okay? Because my path is gamma 1 composed with gamma 2, juxtaposed with gamma 2, right? And therefore this is all right. Okay, on gamma 1 I have something interesting. It centers around 1, right? Therefore I can think of my function f1 of z equal to z squared plus 1 by z squared. Okay, right? Now what is the domain for this function u1? This is c minus 0, singleton 0, which is c star, right? Now let us look at, therefore if I take any open disk around 1 centered with r such that 0 less than or less than 1, this is completely contained in u1, and hence in particular gamma 1, the trace of that is contained in u1. You understand? Therefore this one I can write this as integral of f1 of z by z minus 1 dz over gamma 1. This integral equal to this. Are you following? Similarly, for the similar reason, let us look at f2 of z. f2 of z I can write, see now over gamma 2 it goes around 0, 1 is not affected, therefore I can think of this z squared plus 1 by z minus 1 in where c minus singleton 1. This is my u2, right? And let's look at that trace of gamma 2 is also contained in u2 as I explained there. Therefore that fellow is gamma 2 of f2 of z by z squared. Yeah, therefore by Cauchy integral formula, remember this goes in the wrong direction, therefore I have to put a minus 2 pi I. Okay, this is clockwise direction, you see that, minus 2 pi I into, this is by z1, therefore it is f1 at 1. f1 at 1 is what? f1 at 1 is, this is 1 plus 1 2 by 1, therefore 2, therefore 2, this is 2, therefore I get a minus 2 pi I. Okay, plus then I have to look at f2 of z and compute its derivative, right? This is going to be 2 pi I. This is the anti-clockwise direction, Therefore it will be 2 pi I into f2 of dash at 0. Okay, let us compute that. What is f2 of z? f2 of z is z squared plus 1 by, I hope, z minus 1. Therefore the derivative is going to be 2z by z minus 1 plus z squared plus 1, and there is a minus sign, and minus 1 into z minus 1, yeah, whole squared. I hope I did it correctly. And this is f dash of f2 dash of z. Therefore f2 dash of 0 is just minus 1 by this is 1 square, that's just minus 1. Therefore, okay, integral of our gamma 2 portion, that is f2 of z by z squared, is minus 2 pi I. Therefore integral of f over gamma is minus 6 pi I. Please go through the second example. I made it slightly more complicated so that how to recognize, how to manage things the way we want. Okay, that will be a very good thing. And there is a possibility in my hurry to explain. Okay, I might have made some sign mistake here or there, computational, taking the derivative, etc. But I'm sure you can do better. Do it. Okay, let's go back. Okay, so pause, review, proceed. Okay, right. Now let's go to a theoretical question. Suppose f is holomorphic from U to C, holomorphic, okay, with the standard assumptions, etc. Let us assume f of z is 1 by 2 pi I integral of f of w, f dash of z is w minus z whole squared, right? I want to know whether it's equal to 1 by 2 pi I f dash of w by w minus z. Are they equal? Okay. Now one can, there is a calculus method. Calculus method is, okay, look at f dash, and according to the Cauchy integral formula, this is nothing other than f dash at z, and this is Cauchy, this is by Cauchy integral formula for f dash, and this is Cauchy integral formula for derivatives, for, okay, for apply for f, therefore f dash z, therefore they are equal. Do you follow that? Okay, but there is a subtlety, yeah. But if I want to apply Cauchy integral formula, what should I know about f dash? It should be holomorphic. Do I know that? But luckily we proved, because any holomorphic function is analytic, and hence this result is true. You see that? This is the difference between analysis and calculus. You simply compute. Huh? There is a formula, you just plug it in and get it. That's where you get. You follow that? There is a subtlety. So I needed the fact I can apply Cauchy integral formula for f dash. If I have to apply Cauchy integral formula for f dash, then it should be holomorphic. How do I know that? F dash is derivative of a holomorphic function, and hence any derivative of any holomorphic function is also holomorphic. We proved it. Isn't it beautiful? Think about it. Okay, now let's go to the next one. Okay, so I had a few things which I wanted to write. Typical example I had worked out. Yeah, now there is next one, what is called Cauchy's estimate. This is utterly trivial. Okay, this follows by something like ML inequality with our standard notation. Keep the standard notation for Cauchy integral formula for circular path. Okay, then what you have is f1 dash of z is n factorial by 2 pi I integral over gamma r. Okay, gamma r is something f of w minus z to the power n plus 1. If you want, make it z naught also, I don't care. This is therefore my gamma r of t is z plus r e power I t, etc. Right? So let mr be the maximum. I want to estimate mod fn of z. Let me say what I want. I want to find an estimate. So natural thing is I use ml inequality. Therefore let mr be the supremum of mod f w as w is in gamma r. Yeah, and what will be w minus z? That will be r to the power n plus 1. Therefore that will be less than or equal to n by 2 pi I. The length of the thing will be 2 pi r, and this will be mr, and this will be r to the power n plus 1. Therefore n factorial, sorry, so n factorial by 2 pi mr by r power n. These estimates are called Cauchy estimates. So in particular, put cn mod cn is less than or equal to n factorial goes away. Therefore it is 1 by 2 pi mr by r power n. Okay, these two are called Cauchy estimates. So as you can see, this is extremely trivial. This is just a standard, okay, ML inequality applied to the circular path. It becomes, life is very easy. So I got it. But what is the significance and how to use it? These are the two things I would like to talk about. Okay, right. I hope I changed to, yeah, good. See, many times I keep forgetting. You may not know. Almost for every other video I goof up lot of things. Okay, I forget to share the screen, or I forget to start the recording, various kinds of nonsense. Okay, so that's why one needs an assistant to help me in all these things. Okay, come back. So why is this important? Let us recall real analysis. See, if I have a function f from r to r differentiable, okay, if I want to estimate something like fx minus fy, the obvious thing is to use the derivative. So if you want, I can make it take the supremum over z in the interval axy or interval yx, whichever way it is. You understand? So I can estimate the function in terms of the derivative. That's what mean value theorem told us. Okay, that's one of the important aspects of mean value theorem. If you have gone through my real analysis lectures, especially on differentiation, I would explain. Okay, the estimate, it allows us to estimate the thing. Okay, if I want to estimate fx minus fy, natural thing should occur to me is mean value theorem. So I am estimating the variation in the function by derivative. But here what did we have? Look at this cn or fn. These are nth derivative. I am estimating the derivative in terms of the function. Because mn is LUB of mod f of, right, on the path. Are you following? So that is a subtle difference. Notice, okay. So notice the subtle difference. Okay, appreciate this. Now let's quickly do some estimate of this kind. Okay, suppose I have an entire function f from c to c. Okay, then I know I can write f of z as summation c and z power n. This is true for all z and c. Right? Now what does it say? It says that, okay, nth derivative, that is mod cn, is less than or equal to, suppose this function is bounded, that is mod f of z is less than or equal to m for every z. Then that is going to be bounded by, let us go, what is the derivative? 1 by 2 pi 1 by 2 pi m by r power n, right? So if n is greater than or equal to 1, by letting r tend to infinity, then I say for all n greater than or equal to 1, Cn is 0. That means f is a constant. So this is our Liouville's theorem. Yeah. Okay. Another application. Suppose f again is an entire function from C to C, so that for every m there is an r positive, right? So that f of z, okay, no, there is an r positive, so that f of z, okay. Now let me formulate it carefully. What do I want? I want to say it's something of a polynomial, so let me say that, okay, f of z, there exists m positive and r positive, so that for all z with mod z greater than r, greater than or equal to r, modulus f of z is less than or equal to c to the power mod z to the power n. Okay. So where is m here? This is c. Okay. Okay, there exists capital N, let us assume. I'm sorry for the kind of confusion, because I am thinking what should I make sure. So I want to show there is an n, so that f of z is less than or equal to c, less than or equal to c times mod z power n. So perhaps for all z such that mod z is greater than r. This is all I want to see. Okay. There exists n, and a constant positive, so that this happens. Then I want to conclude, okay, f is a polynomial of degree less than or equal to capital N. You understand that? So forget all these things. What is my assumption? There is a natural number n, okay, and a positive constant c, and an r positive, so that mod f z is less than or equal to c times mod z to the power n for all z, so that mod z greater than r. Whatever I wrote is correct. Now I am just writing it up. Right. Yeah, earlier also that's what I wrote. Okay. Is it okay? Make sure you understand this statement. Now how do I prove it? Since the entire, as usual, I can write it as summation Cn z power n 0 to infinity. This is true for all z in C, right? Now let's look at what is Cn. Okay. So what do I know? Yeah. So let us look at the, yeah, right. Let n be greater than n. Okay. Right. Then what do I know about mod Cn? Mod Cn is less than or equal to, okay, and also assume mod z is greater than r. Okay. Right. So I am going to look at something, okay, z here, where mod z is, this may be my r, this is greater than r, right? So on that circle, what do I have? I have 1 by 2 pi into the bound for this. The bound for this, I know what is the bound. Okay, mr, the bound for this, c into mod z power n, right? Are you following? Because mod fz, okay, is less than or equal to c times mod z power n whenever mod z is greater than r, right? Therefore on this, for such z, okay, what do I have? This one. And what is the radius? Radius is, okay, this is, yeah, what do I have to do? I have to take r power n, right? Okay. So this, let us assume this r. For once my r, small r is bigger than capital R, r power n. Yeah, this is true for which n? For all n greater than or equal to capital N. Are you following? Yeah. Now do you see a problem? See this mod z, okay, this I can fix it on capital, okay. Again, this is r. This is because this z is going to be on small r, right? Right. Therefore, this is, let me rewrite C, capital C into mod z here, okay, and here on this is r. Therefore, it's r power capital N. This is r power small n. Therefore, 1 by 2 pi I C into r to the power capital N minus n. Right? Now n is greater than or equal to capital N. Therefore, this goes to 0 as r goes to infinity. Right? So, what do you think I have proved? Therefore, for all n greater than or equal to n, I have proved Cn is 0. Therefore, f is a polynomial strictly greater than n. Polynomial of degree less than or equal to capital N, because I do not know what happened to Cn. Okay, PRP. So these are the typical uses of Cauchy estimate. And the last one is the so-called mean value theorem. We keep the standard notation. Okay, gamma r is z plus r e power I t, or a, let us call it a r e power I t. Okay, gamma r of t. Okay, as usual, bar is contained in u, and f is holomorphic from u to c, etc., etc., etc. Right? In fact, ba capital R is contained and 0 less than or small r. Okay, this is a notation just to make sure that I know what I am talking, I am writing. Therefore, f of a is 1 by 2 pi I f of w by w minus a dw. This is Cauchy integral formula, right? This is over gamma. Now let us write down the path integral carefully. This is 1 by 2 pi I integral over 0 to 2 pi. What is w? W a plus r e power I t. F of gamma t, right, by gamma t minus a, that is your w minus a. Therefore it's r e power I t. R e power I t into gamma prime t, that is r I e power I t. Therefore r e power I t, r e power I t cancels, I cancels with I. Therefore I have 1 by 2 pi integral over 0 to 2 pi f of a plus r e power I t dt. Okay. Now notice that I have f. Okay, this is my, perhaps my a. This is the thing. This is my a, and this is a plus r e power I t for some t. Right? Okay. Now this is, I am taking sum over that. See, what is average? Average of finite numbers alpha 1 to alpha n will be alpha 1 plus alpha n by n, right? So the average in the integral will be f of x from a to b dx, and how many elements are there? I will use as length b minus a. This I call as average. Average of f on the interval a b, right? Therefore this is the average or the mean value of f over the circle gamma. You understand? But that is equal to f of a. So whatever circle I take, okay, As long as it's contained in that, okay, the mean value will always turn out to be FP. Okay, this is something very surprising. We will see, we will have use for this. So I it's important for local study properties of holomorphic functions. That is going to be the next series of lectures. Okay, Cauchy integral formula and some of these things which I derived, they will play a very important role. So please go through that. Okay, mastering complex analysis means mastering how to work with path integral, how to use Cauchy integral formulas of various kinds, and how to derive the results you want. Okay, please learn that. We will meet again.